scientists looking at the different issues. Our first presentation was done by Anastasia Slovina from Russia, and Anastasia talked up to us about the experience of using bioshophite, which is a mineral used very much in kind of complementary medicine. But then also we had a fantastic talk by Patricia Ventura about volcanic emissions that what the studies they are doing in the University of Azores in this particular area of research. Our friend Rufus Cheney from the Department of Agriculture gave us a fantastic talk last time about the human risk from cadmium exposure, dealing with soil quality and the research, and also with the type of regulations that we need to understand and put in place to reduce the type of exposure to cadmium. And there was a seminar that I gave to the organization GeoLatinas on medical geology. Today we are extremely honored and privileged to have our dear friend and colleague, Professor Claire Horwell from Durham University, from the Department of Geosciences at Durham University. Claire is a professor of geohealth at Durham University, and her PhD is in volcanology. She has one of the unique contributions that Claire has done in this field is that she has created a global network of scientists looking at this particular area of volcanology and the issues dealing with the health effects and how to prepare for these natural events. I am very delighted to have Claire today with us, and hope that this opportunity will open many other doors for geoscientists, for public health scientists, and for toxicologists, and even epidemiologists to look at the issues of volcanic dust emissions, and even talked about the impact to society. Societal the impact that this type of natural event will have in society. So with that, Claire, I'm really proud and honored to have you here today. And I would like to personally thank you for taking your time. I know that you are a very busy scientist and you are very busy at the university, and we appreciate highly that you took your time to be with us today. Thank you so much. And now I would like to move the floor to you.
Thanks so much, Jose, and also many thanks indeed for inviting me. I mean, quite the contrary, it's an absolute honor to be part of your seminar series, so thank you very much. So I will now share my screen. Oh, great, your one's gone.
There we go.
Okay, is that all good?
Yes.
Perfect. Okay. Well, so I wanted to give a talk today, which is very close to my heart, really, because it really reflects the journey of my career, which I think maybe only in very recent years did I really understand that, as well as being a volcanologist and an environmental scientist, I'm also a disaster scientist, and I work on, humanitarian relief in some ways, trying to protect communities from volcanic eruptions. And I think that's a very important concept in medical geology and in environmental health, thinking about not only what is happening to our Earth and how it's impacting society, but what we can actually do to then protect society. So I'm going to talk about the challenges of chronic and delayed disasters, which is quite specific, and I'll explain exactly what I mean by that. And I'm going to do that through the lens of understanding volcanoes, their eruptions, and their subsequent health impacts.
Claire, may I ask you something? Is there a possibility that you can go into full screen of the presentation?
Right. You're not seeing that. Okay, that's interesting. Give me a
We're
minute.
seeing two views, your
Yeah,
notes
views.
and the slide. Okay.
Okay, I'm going to try again. That's very strange. Earlier on, it was.
If you go into the PowerPoint presentation up, you might see.
How about now?
Yeah, perfect.
Perfect.
That's perfect. Perfect.
That's strange. We tested it earlier and it was perfect. So I don't know what had changed. Okay. Can you see that I've changed my slide? Okay, we're good.
Yes,
Thank you.
do.
Wonderful. Thank you. Okay, let's start again. So I think, because we've got a broad audience of people interested in different aspects of medical geology and environmental health and geohealth, I'm going to start with some basic descriptions. So we're going to start with actually what is disaster risk, because ultimately when we're talking about health, we're talking about the risk to communities. So actually the United Nations Office for Disaster Risk Reduction has a definition for disaster risk, which is the potential disaster losses in lives, health status, livelihoods, assets and services, which could occur to a particular community or a society over some specified future time period. Now you'll see that I have highlighted some words here. I've highlighted potential and future, because the point about risk is that really it's unknown and we're having to make calculations about what could happen. And with health as well, there are immediate effects and there are effects that can happen way into the future. And that's really what I'm going to delve into here. So first of all, if we think about volcanoes, we need to think about the timescales over which they erupt. And when we think about volcanoes, we can also put them in the context of other natural hazards, because that helps us to understand where they sit. So here is a diagram which shows a number of different particular hazardous events. We're looking at hurricanes, volcanic eruptions, tsunami, earthquakes, and flooding. And you'll see that for most of these natural hazards, the hazard itself takes place over a timescale of sometimes hours, maybe days, and occasionally into weeks and months, especially for flooding and etc. Now, the thing about volcanoes is that they sit quite differently. While some eruptions are indeed over in just seconds or even hours, days, or weeks, many eruptions can actually continue for much longer than that and can enter not only time frame of months, but into years or even decades as well. So if we think about eruptions over the past couple of years, Taal in the Philippines in January 2020 was erupting just for a matter of days. The La Soufriere in St. Vincent erupted over weeks to months. The same for La Palma in the Canary Islands. But there are other eruptions, such as Kilauea volcano in Hawaii, which continue for decades. So the eruption between 1983 to 2018 was obviously quite unprecedented in its length. The Soufriere Hills volcano, which I'll talk about later, also has been erupting from 1995 and is still considered active now. So it's really, really hard for us to predict and understand exactly how long volcanoes are going to erupt for. And because of that, it's really hard for us to understand when and during what time period the health impacts could happen. So I put together a couple of diagrams to try and demonstrate this. So here we've got a timeline, the blue line heading to the right is in years. And we can imagine that an eruption might happen and it might be quite a one-off event over just a few hours or days. And therefore, the hazard and the exposure for the communities is going to be a very acute event. So sudden onset and short duration. But there are some eruptions, as I just explained, which can carry on for years or decades. And in this case, you have a persisting eruption or exposure for a very long time. And this may be frequently reoccurring. And what you see here are these kind of little suns with clouds. That's to demonstrate that sometimes with volcanic emissions, the volcano itself doesn't have to be erupting, but the hazard can still be airborne. So we still have volcanic ash and gas in the air, despite the volcano being in a quiet period. So these kinds of chronic exposures can continue for many, many, many years. Now I'm overlaying onto this same diagram now the concept of impact, which I've added up here with a little eye in a circle. So with an acute hazard and exposure, the impact will be pretty much immediate. With the chronic persisting eruptions or persisting exposures, then your impact again will be persistent over a long time frame, and maybe it might be cyclical, or you know, there's going to be different patterns of exposure, but people may well be exposed for many years. But there's a third type of impact that I'd like to introduce, which is the concept of a volcano being erupting, maybe just for a short amount of time, or maybe it may be quite a chronic eruption, and we might have impact during that period. But actually, the impact that we're really worried about could be postponed or deferred until much later in the future, and when the volcano is no longer erupting. Now, you might wonder, how on earth can this happen? How can you have no impact and then it suddenly appear years ahead? And that's what I'm going to come on to later in this talk. So let's go back to the timeframes of exposure and eruption. This is the example now of the Soufriere Hills volcano, which is a volcano on the island of Montserrat in the Eastern Caribbean. It's a volcano that I have studied for many years. It started erupting on the 18th of July, 1995. And really, it was erupting until 2011, although it is still considered active today. So roughly 16 years of eruption. And you can see that during this time, there was fumarolic activity, there was deformation, there was seismic activity. But the actual extrusion of lava, either explosively or passively, actually took place in 4 phases, as you can see on this bottom row here. Now, you can imagine for the communities on that island that at the end of phase 1, when the volcano was no longer extruding lava, they would have all breathed a sigh of relief and hoped that that was the end of the eruption. But then it started again, and then it started again and again. So you can imagine the kind of disruption that that causes for a community, but also the concerns about chronic exposures. So how can you actually assess a disaster risk when the length of the eruption is just completely uncertain? The size of the eruption can be just very variable as well. And in fact, the scale of an eruption can change on a daily basis, depending on the magmatic conditions. There are also multiple different hazards that emanate from volcanoes. You can have all kinds of flows, like pyroclastic flows, lahars, surges, etc. There can be explosions with ballistics and also pyroclastic flows associated with those. There can be ash and gas release, usually during explosions. And there can be all kinds of cascading or secondary hazards as well. For example, tsunami, earthquakes, fires, building collapse, etc. And because of all these multitude of hazards, there are also a multitude of impacts to society. And these are not just to humans, of course. The impacts are to animals, to buildings, to infrastructure, to all of our utilities. So there is a vast amount to consider when we think about disaster risk of volcanoes. And that is without even considering the societies that are being impacted. We're barely even thinking yet about the vulnerability of those societies and about what exposure they're actually getting. So obviously I can't possibly consider all of that in one talk. So for this talk, I'm going to focus just on a single hazard, which is the effects of volcanic ash, and a single impact, which is the health impact of inhaling volcanic ash. So I'm aware that some of you may not have studied volcanology, may not really be very familiar with what volcanic ash is. So just to clarify, we all understand that it's a powder made of rock, but the actual description of it is particles less than 2 millimeter in diameter, which will be made of fragmented magma, crystals, and also the edifice. So the volcano itself will kind of blow itself apart to some extent and be incorporated into the ash. You can see here in these images just a couple of examples of ash in our landscape, one in Keludin, Indonesia in 2014, and one very recently from La Palma in late 2021. Obviously, volcanic ash in our landscape is going to have a huge impact. And you can imagine that if you wake up and find that your local volcano has erupted, or suddenly you're surrounded by ash from an ash cloud, one of the first things you're going to wonder is it harmful for me to be breathing this ash? Because the ash may still be falling, it's very likely to still be at least airborne and being remobilized by vehicles and by traffic. And so you're going to be breathing in the ash probably in every breath you take. And that can be a very, very scary experience for communities who've never experienced ash before. So one of the main questions as a scientist that I've been trying to answer through my career is it actually harmful to breathe volcanic ash, to inhale it? So I'm going to focus on inhalation rather than the effects of ash on the skin or the eyes or any other part of the body. One of the first things that we're concerned about when we look at inhaling volcanic ash is how large are the particles. Now we know that particles less than 100 micrometers in diameter, roughly, can enter into the respiratory system. So we also know that particles much, much smaller than that can get deep into our lungs. So let's have a look and try and imagine what those actually look like. So here we've got a diagram which shows a human hair. Okay, this is a kind of drawing of a human hair, and the width of a human hair is perhaps maybe 50 to 70 micrometers in diameter. And you know, if you look at one of your hairs, they're pretty thin, aren't they? If you were to kind of look at the end of your hair, it's kind of almost hard to be able to see it, it's so small. So 50 to 70 microns is definitely the size of particle that we can breathe in, at least to our upper lungs. But there are much, much smaller particles that can get deeper into our lungs. And these are known as PM10. And you may well have heard of these expressions from discussions around air pollution from urban pollutants or wildfires, for example. So PM10 are particles sub 10 micrometers in diameter. And so obviously you can fit around 5 of those across the width of a 50 micron hair. And then it can go much, much smaller than that. And we also tend to talk about PM 2.5, because this is the really tiny size of particle that can make it very deep into the lung, where we're most concerned about health impacts. So if we actually take a look at the human lung, you're probably familiar with the concept that we have a windpipe or a trachea that we bring air into our lungs through when we breathe in. And so the larger particles of sort of 100 micrometers or so are going to get stuck in the mouth, in the nose, and in the upper throat. And the particles sort of 10 to 100 micrometers probably won't really make it deep into the lungs. But particles roughly 10 or so micrometers in diameter will make it into the bronchi. So that's the kind of main tubes at the top of the lungs, and may well deposit, as you can see from this pink line here, on the walls of the bronchi and the bronchioli. And this part of your lungs is the part that's most affected if you have asthma and bronchitis. So the impact of particles which may have an acidic coating on them landing on the lung can be to exacerbate existing symptoms of asthma and bronchitis if you're already susceptible to those diseases. But as I mentioned, we're also worried about the particles that can make it even deeper into the lung. And when you look at the lung, it's a bit like a tree, and it branches and it branches and it branches until eventually you reach tiny air sacs at the end called alveoli. Now, this is a photo on the right-hand side here, taken with an electron microscope showing the structure of alveoli. And I've superimposed these little red particles here to try and explain that it's possible for these tiny particles, sub 5 micrometers in diameter roughly, to make it into our alveoli. Now, a bit of a biology 101 here, the alveoli is where we conduct gas exchange. So that means that the oxygen that we breathe in is transferred from the alveoli into our veins and our blood system, the capillaries surrounding the alveoli. And in exchange, carbon dioxide is given up from the blood system and back into the lungs through the alveoli. So this is a critical part of staying alive. We have to be able to conduct this gas exchange process. And if our alveoli become full of particles, then that can be extremely dangerous. Basically, what can happen is that over time, our body's defenses, so we have cells which can come in to try and remove these particles, they become overwhelmed, either if there's far too many particles or if we have particles of a particularly toxic nature. And so in the deep lung is where these diseases may occur. And this is one thing we're worried about with volcanic ash, is that there could be generation of these diseases from communities who are very highly exposed to ash. Now, the thing is that these diseases don't just start immediately upon exposure. They may take very, very long exposures to actually occur, or they can have relatively short exposure, but there can be a delay in the disease actually manifesting and showing itself. And that's a little bit the same with, for example, lung cancer and smoking, is that often you may not realize that you're ill until many, many years down the line, even if you've stopped smoking. So now you start to understand the concept of how we can have a chronic disease that may be delayed or deferred, so that basically, even though your exposure to the eruption may have stopped many, many years ago, you might not actually come down or kind of be diagnosed with a disease for many years, possibly decades after. Now, the problem is that with volcanic eruptions, there can be hundreds of thousands or sometimes even millions of people exposed to the ash. So obviously it is a great concern to think that when a volcano erupts, that in a decade, there could be the potential for many, many, many people to become ill from that exposure. And this is something that we're very concerned about. And this is why a lot of effort has been put into researching this over the past 40 years or so. So I mentioned that we may be particularly worried about certain types of particles that may be particularly toxic. With volcanic ash, we think that one of the main toxic particles could be crystalline silica. So crystalline silica is made of SiO2, silicon dioxide, in crystalline form, obviously. And oh, sorry, there's a lot of noise. Somebody's not muted. Okay, I'll try to continue. Maybe if Jesus could mute everyone.
Teresa, can you mute your microphone?
Yes, I will turn it off.
Yeah.
Okay. So, yeah, crystalline silica, we know from industrial exposures. So that means people who are working in occupational settings where they are exposed to crystalline silica. And that's usually miners and quarry workers who are actually grinding rocks made mainly of quartz. We know that these people can get extremely ill by being exposed to crystalline silica. So we're concerned that some volcanoes also generate crystalline silica. While some volcanoes do produce quartz, there are other volcanoes which produce a different kind of crystalline silica called cristobalite. And actually, we've come to realize that these are the volcanoes we need to be particularly worried about, because the ash coming from these volcanoes can have up to around 30% cristobalite. So it's a very particular kind of eruption that produces cristobalite. For the main part, it tends to be an eruption where there is a lava dome. And in the next slide, I will explain that. But just to show here, I have some beautiful electron microscopy images of cristobalite. Here is a crystal of cristobalite sitting within basically a bubble within volcanic lava. And you can see it sitting on a bed of other crystals. And here is a cross section through a bubble. And you can see how the cristobalite is a beautiful hexagonal shape sticking out into the bubble with the other crystals around it. So what do I mean by a volcanic dome? Well, some eruptions produce very red, runny lava, like in Hawaii. Other eruptions, like at the Soufriere Hills volcano on Montserrat, produce a much more sticky, viscous lava. And when it erupts into the volcanic crater, basically sometimes it may explode with the pressure, but at other periods in its eruption, it might actually kind of ooze out of the volcano, a bit like squeezing a tube of toothpaste. And that very sticky lava is almost like rock when it erupts, and it tends to just build up in a big pile within the crater, as you can see here. This is the conduit, and here is the crater, and the red shows the lava coming out. So I mentioned the Soufriere Hills, and this is what the volcano looked like. What you can't see is that the crater of the volcano is actually kind of roughly where my mouse is. I'm hoping you can see the oh, excuse me. I'm hoping you can see my mouse. So it's kind of in the top half of the volcano. And what you're actually seeing here is that this entire crater of the volcano has been filled up with a huge mound of lava. Now, these mounds, as you might imagine, are relatively unstable, and they quite frequently collapse, and that will be due to, well, basically the lava becoming unstable due to more lava being pushed up underneath, but also it can collapse due to heavy rainfall or earthquakes, etc. So what you see in the top photo is you see the Soufriere Hills volcano with a large debris fan coming from it out to sea, which is where the dome has previously collapsed. And when it collapses, the rock fragments and it forms pyroclastic density currents, which are also known as pyroclastic flows, which zoom down the slopes of the mountain. And as that happens, very fine-grained ash is lofted away from the volcano and is carried by wind, and some of it will disperse and deposit on local communities. So that's how communities get exposed to the ash from lava domes. But what about the cristobalite? Well, when the dome is sitting here, and you can imagine it slowly cooling, it comes out at extremely hot temperatures, and over time it cools. And you can see in the image that you can see vapors and fumaroles on the slopes of the volcano. And so basically within the conduit, there are still gases coming. These travel through cracks and holes and bubbles through the dome itself. And as that happens, one of the processes that can happen is that cristobalite can be deposited and kind of grow within these cracks. So I said that we're worried about crystalline silica because we know that in industrial circumstances, it can cause horrific diseases. So what actually are these diseases? Well, the first one is a disease called silicosis. Sadly, this is a fatal inflammatory and progressive scarring lung disease, which can take 10 to 20 years to incubate. So it can be a couple of decades before you're actually diagnosed with the disease. So in the previous slides, I showed you an electron micrograph of the alveoli. Now we're switching over to a light microscope image. And here you see the alveoli again in the left-hand image. And you can see that when you look at a thin section of alveoli, the walls between the sacs, so the kind of alveolar spaces, the walls should be lovely and thin. And this is what you need for gas exchange. In the middle image, what you see is what happens after someone's been breathing in a lot of dust. And you can see that the walls of the alveoli are thickened. And in fact, you can see that there are black dots. And I'm not sure if this particular image is of silica or of coal dust or some other dust, but you can basically readily see the dots of particles that have been incorporated into the cell walls or are sitting against them. And basically an inflammation process is happening where the body is not able to clear these particles. And sadly, over time and exposure, basically a process of scarring happens effectively, which can form these large silicotic nodules, which you can see in the right-hand image. And these are effectively made of collagen. And once you have these nodules, they can't be removed. And also, you can imagine that you can't breathe properly if your lungs are full of these nodules instead of full of nice, healthy, open air sacs. So silica is unfortunately also a carcinogen, and it was defined as such by IARC, the International Agency for Research on Cancer, in 1997. It was defined as a group 1 carcinogen, which is the most dangerous kind. You can see here, a slightly gory image of a lung with a large tumor in it, a lung cancer tumor from, in this case, a coal miner. But when IARC made their declaration about the carcinogenicity of crystalline silica, they put in a rather major caveat. They said the carcinogenicity to humans was not detected in all industrial circumstances studied. The carcinogenicity may be dependent on inherent characteristics of the crystalline silica or on external factors affecting its biological activity. So what this effectively means is that silica seems only to be toxic and pathogenic in some circumstances and not in others. And this became known as the crystalline silica enigma. And it was known for lung cancer, but also later it was realized that the same went for silicosis as well. So it became really important for us to understand whether crystalline silica in volcanic ash could actually cause disease or not. And one of the main ways that we study this, of course, we try to study communities, but kind of for shorter term studies, we might do toxicology. And in particular, we might do in vitro toxicology on cells. And a number of in vitro toxicology studies have been done now on volcanic ash, starting in 1980 with the eruption of Mount St. Helens. The particular graph I've chosen to show you was by one of my PhD students, David Danby. And he looked at the impact to cells of being bathed in volcanic ash, but he also used a positive control, which was a very toxic quartz called DQ12, and what is supposed to be a negative control, which is titanium dioxide. And what you're looking here is LDH release is really a sign that cells are in distress or are even dying. So it's a signal given out by cells. And so what we're looking at on the x-axis is particle dose, and you can see that very rapidly the cells become distressed with DQ12. Now it is slower, and there's less of a response for TiO2 for what is supposed to be a negative control, but still the cells certainly reacted to it. But for volcanic ash, as you can see, there was basically no reaction. Now we've seen this again and again and again. This is called a cytotoxicity assay. So we're looking at cell death and cell distress, and we've looked at many, many ash samples over the years. And for the most part, volcanic ash seems not to be cytotoxic. Now we do sometimes see some toxicological response. It tends to be what's known as a pro-inflammatory response. And inflammation can be a precursor to cancer. So we're not saying here that volcanic ash is not toxic, but what we're saying is that it doesn't necessarily seem to be toxic in the normal ways that we might expect particles to be toxic. So why might that be? So you'll remember that IARC said that there could be inherent characteristics of the silica which might be somehow controlling its toxicity and moderating it, either making it more or less toxic. And we'd noticed, or rather I'd noticed during my PhD, that when I looked at crystalline silica particles of cristobalite in volcanic ash, they weren't pure SiO2. They should have been. When you look at quartz, as you can see in this diagram down here, the little white triangles, they are basically 100% SiO2. That's what you would expect for a crystalline silica polymorph. But actually cristobalite has got quite an open crystalline structure, which is known to let some impurities into that structure. And actually, for example, aluminium can actually substitute for silica within crystalline silica structure. And so what we found in this study, and you don't need to worry about the different kinds of cristobalite, but basically we found that cristobalite could contain up to around 3 weight % aluminium and also 1 to 2 weight % sodium. So these were not pure crystals, and we wondered whether that might actually have an impact on its toxicity. So another one of my PhD students, Claire Natras, did a study to try and work out whether that might be the case. And so we actually simulated cristobalite in the laboratory. We grew it in the lab, and we either kept it pure, just SiO2, or we doped it with impurities of aluminium and sodium. And so again, here we're looking at cytotoxicity. And again, here we have this very toxic DQ12 standard. And you can see that this standard had almost 100% toxicity to the cells at the dose that we used, which is given down here. Now, the white bars that you see in this graph, this is the pure cristobalite that we manufactured. You don't need to really worry about, they're just different conditions and timeframes that we manufactured it under, but basically they all had roughly 60% cytotoxicity. But when we doped the crystalline silica, the cristobalite, with aluminium and sodium as it was growing, so that the aluminium and sodium were incorporated into the structure of the crystal, we actually found that the cytotoxicity dramatically increased, especially when we had, so this is 1% aluminium, 2% and 3%. So 2 and 3% in particular had a dramatic impact on cytotoxicity. So this made us realize that the inherent characteristic of the ash, that it is impure, could actually be impacting its toxicity. But you'll remember that IARC also said that there could be external characteristics which also might impact toxicity. And one of the interesting things about lava domes and their collapse is that, of course, when you fragment a huge lava dome, you wouldn't necessarily expect the cristobalite to break off into its individual particle, because of course it was part of a dome. It may have been in a bubble, but it was still attached to the wall of the bubble. So what we found out actually, when we looked at the crystals in detail, and here this is a tiny, tiny crystal, it was very unusual for us to see a particle like this top left one, which is pure crystalline silica, pure cristobalite. Mostly when we looked at the particles, we saw hybrid particles, which were partly cristobalite and partly dome rock. So for example, image B here, on the right-hand side, you can see a nice piece of cristobalite, which would have been sticking out into a bubble, still attached to its piece of dome rock. And again here, this one here on the bottom right is almost completely covered in bits of dome rock. And this one here, the cristobalite was made with this by a slightly different kind of process, which I haven't explained, called devitrification. And you can see that the cristobalite and the crystals surrounding it are actually kind of intergrown. Anyway, the point is that these are insoluble particles in the lung. So if the lung cells are going to react with the particles, it's going to be to the surface of the particle. So if the surface of the particle isn't actually cristobalite, or it's mainly a different mineral, probably a more inert mineral like volcanic glass, then we're going to see less of a toxic response. So that kind of explains the story of crystalline silica in volcanic eruptions. And I've worked on this for many, many years, and the story is not yet finished, but that's kind of where we've got to in our understanding. But my research also found that there are other aspects of volcanic ash that we maybe need to be concerned about chemically in eruptions. And one point that we discovered was that, well, there are different kinds of magma, and obviously there are those kinds of magma which contain a lot more SiO2 and which are going to generate crystalline silica. But at the other end of the spectrum, there are quite low SiO2 magmas which actually have a lot of iron in them. And for example, Kilauea in Hawaii is an example of this. It generates basaltic magma, which is iron rich. And it turns out that iron can actually cause toxicity. So in the lungs, iron can react with hydrogen peroxide, which is naturally available or can be made through Fenton reactions. And when iron and hydrogen peroxide react together, they can generate the hydroxyl radical. Now, the hydroxyl radical is very, very dangerous. Basically, it's missing an electron, and so it's very reactive, and it tries to grab electrons to complete its bonds from whatever's around it. So in this case, probably the innards of cells. And when that happens, it can cause oxidative stress in the cell, and it can damage DNA. And this is part of the early process that can lead to cancers. So we've seen in the laboratory that ash can definitely generate hydroxyl radicals, and particularly iron-rich ash. We've seen the Etna volcano seems to be particularly concerning in this respect. But we don't yet know if this could translate to disease. So moving on, there are other impacts that volcanic ash could actually have to human health. We're worried about the interaction that ash could have when it falls into an environment which is already highly polluted. So let's take the example of a city like Mexico City, for example, which potentially has poor air quality, and then you get an eruption from Popocatépetl, which deposits another pollutant into that environment. What does that mean for people who are already exposed? Are they more susceptible then to having impacts from that kind of extra exposure? So my PhD student Ines Tomaszek did experiments on this, where she mixed, or rather she exposed cells to volcanic ash and also to diesel exhaust. And indeed, we did see an additional pro-inflammatory response in those in vitro toxicology experiments. But there's plenty more work to be done in this area. I think I'll move on now, but the other thing that we sometimes measure as well is the impacts to drinking water. So this moves a little bit away from respiratory hazard. We're worried about fluoride and some other elements and how they may lead to fluorosis, but I think I'll move on and stay with the respiratory for now. So going back to the health impacts of inhaling ash, if you remember back to my lung diagram, we are worried about well, for healthy people, mostly they're going to experience an irritation of the airways. They may get cough, they may get sore throat and phlegm. But for people who already have respiratory disease, we're likely to see acute exacerbation of their symptoms. So asthma, bronchitis, and possibly pulmonary and other cardiovascular symptoms as well. But what about the chronic disease? And what about the idea of a delayed disaster? Are we going to get people coming down with silicosis, lung cancer, also tuberculosis, and other diseases that are basically related to very high exposures to mineral dusts? Well, actually, currently, we have no evidence that volcanic ash does cause these diseases. This is quite contrary to what you'll read in the media, where almost every eruption, the media will leap on some article where they've said that volcanic ash causes silicosis. We just don't have the medical evidence for that. There have been some anecdotal reports, but conducting studies is very, very, very challenging. So the lack of evidence is not necessarily because volcanic ash does not cause these diseases. It may simply be because we haven't done the medical studies at the right time and in the right place. So there are different kinds of medical studies that we could do. We could do clinical medicine, but of course this is going to take years to decades because it can take that long for the diseases to manifest themselves. The same really goes with epidemiology as well. We can retrospectively look back at an eruption, but that also has its challenges because communities move on and it's hard to track cohorts over many decades. And we can try in vivo toxicology as well, which is where you do experiments with animals instead of with cells. But this is not an easy process, and also it's difficult to know how transferable the results are to humans. So have the long-term clinical studies actually been undertaken? The answer is a few have. The first one was undertaken following the Mount St. Helens eruption in 1980, where a 4-year study was conducted on loggers by Sonia Buist and her colleagues. Since then, very, very few studies have been done. They've been attempted at Soufriere Hills on Montserrat, but elsewhere around the world, almost no chronic long-term studies have been done. So we are still very much in the dark as to whether there are delayed illnesses. It's one of the reasons why so few are done is because they're so incredibly hard to conduct. As I mentioned, it's very, very hard to follow a cohort over decades. Often the populations are very small, for example, on volcanic islands, or they're very transient. People leave because of the eruption. They may even be permanently evacuated, and new communities can come in to help rebuild. The eruption itself may not be long enough. It may be impossible to get funding for that kind of long-term study, and there may simply not be the political support for it either in countries which already have a huge amount of problems to deal with. So can we maybe use analogues from other kinds of pollutants, and can we say that volcanic ash might be like those pollutants? Well, there was a step towards this in some ways in 2012 when the World Health Organization produced this report on the top right here called REVIHAP, Review of Evidence of the Health Aspects of Air Pollution. this report said for the first time, really, that both urban pollutants and crustal materials, which would include volcanic emissions, could cause short and long-term diseases and death as well. So these are mainly respiratory and cardiovascular diseases and deaths, but also related to long-term exposure, and particularly to the very, very fine particles. A whole range of other health outcomes were also listed based on this big meta-analysis of thousands of studies, including atherosclerosis, adverse birth outcomes, childhood respiratory disease, neurodevelopment issues, cognitive function, diabetes even. So basically, WHO was saying that we should assume that particles from volcanoes as well as from urban pollutants can cause this wide range of diseases. And if that's the case, then we could use all the air pollution, urban air pollution studies as an analog. The problem is that when it comes down to it, we know as scientists that the composition of ash is completely different from urban pollution. And we see in toxicology studies that the outcomes are different as well. So much as WHO has said that, we really don't think at the moment, we don't have enough evidence to say that we think volcanic ash can actually cause this range of diseases. So if we can't do chronic studies and we don't have the evidence, what else can we do to try and understand the potential risk of these chronic diseases? Well, there are a number of different kinds of studies that we can actually do during the crisis itself and in the weeks to months afterwards. So more kind of in the acute phase, but which can give us some kind of clue as to the potential for long-term impact. So first of all, we can do exposure assessments. And all of these, sorry, I should say, all of these take hours, days, or maybe weeks. So much, much faster than the other kinds of studies. So yeah, we can do exposure assessments where effectively we're doing air quality monitoring, either in an environment or personal monitoring, as you can see up here, of particular occupational groups. We can do syndromic surveillance, which is basically immediate monitoring of any health impacts of an eruption. And some countries have syndromic surveillance set up anyway as part of their health response system. For example, in the UK, the NHS is constantly monitoring for outbreaks of communicable diseases. And these can be adapted for the volcanic risks that we're concerned about, some more respiratory problems. But sometimes these aren't available and they may need to be set up at short notice. We can do in vitro toxicology, mineralogical studies, and geochemistry studies of the kinds that I've just explained to you, looking at particle size, crystalline silica content, leachable elements, etc. But is it actually possible to do these kinds of studies in a crisis? Well, the first thing to say is actually that the health impacts of inhaling the ash is rarely the primary health-based concern. Of much greater concern is going to be how people who have been moved from their homes and put into shelters, etc., are faring. Do they have enough clean water? Do they have enough food? Do they have, is there a system set up to try and monitor communicable diseases? So this is often the very first priority. This is what we saw in St. Vincent last year. Absolutely, the health response was based on the people who had been moved from their homes and checking that they had enough supplies to stay healthy. But if there is going to be a response related to the hazard of the ash, then there are all kinds of questions which often are not asked in advance, but it would be brilliant if they could be. Who is going to set up this syndromic surveillance or epidemiological study? Who is going to do the air quality monitoring? Who is going to collect the ash and who's going to analyze it? And these kind of things are just almost impossible to actually sort out in a crisis. And if you try to do it that way, it delays the response considerably. But of course, there are also logistical issues like airports being closed, which means that it can be very hard to get ash from the location to laboratories to actually do this kind of health response. So the upshot is we can rarely get answers quickly, and especially not in the time frame of the acute exposures. So where are we if we try to summarize this? Do we think that volcanic ash is a chronic health risk? Well, going back to the Soufriere Hills eruption on Montserrat, the UK government was terrified that this island that they were responsible for, because Montserrat is a UK dependency. They were terrified that the communities on this island could get a terminal disease in 30 years' time. It was a very, very concerning time. There'd been nothing like it really since the 1980 eruption of Mount St. Helens in terms of volcanoes that we knew had a high crystalline silica content. Now, without medical studies being set up, it is still impossible for us to know if this is going to happen. There were actually multiple medical studies done on Montserrat. There were X-ray studies, clinical studies done of children and outdoor workers. There haven't been any for a while. So the initial results were good, but you wouldn't necessarily expect to see silicosis showing up in X-rays after the first 10 years, let's say, or sorry, within the first 10 years. We also cannot be necessarily completely confident in our laboratory results, especially the toxicology ones. There are multiple mechanisms that might induce disease, and they cannot all be studied in the laboratory. So we know about some inflammatory markers that we can measure, but there are no doubt other mechanisms that we haven't yet understood. And in fact, we see signs of that because we've done toxicology studies on Soufriere Hills ash, which is cristobalite rich, and Iceland ash, which has no cristobalite in, and both types of ash had a pro-inflammatory response, and we don't understand why. So there's still a lot of research to be done. And of course, most eruptions aren't even studied at all. So the answer is that we just don't know if volcanic ash can cause these acute, chronic or delayed diseases. And because of that, we have to take a precautionary approach to make sure that communities are going to be protected just in case there is the potential for these long-term diseases. So that brings me back to an image that I showed you, or a slide that I showed you right at the start of this talk. On that slide, the question that these communities were asking was, is the ash harmful to breathe? But I guess what I've come to realize in my career is that we can't just study that. We also need to study how to actually protect these communities, because we're not really sure if the ash is harmful to breathe or not. So about 5 years ago, my research direction changed a bit, and I started focusing on protection and prevention of future health disasters. I was lucky enough to get a big project funded on this, and we looked at the effectiveness of different kinds of types of respiratory protection for communities against volcanic ash. Now, this was pre-COVID, so at the time I was one of the few people in the world who was actually looking at respiratory protection for the public. And of course, the results we found for volcanic ash are actually exactly the same as you would expect for any particulate, including the kind of aerosol particles that COVID is carried in. So the results that I'll tell you about now will not be a surprise to you, because now we've all been through this process of being informed about what kinds of masks, etc., are effective. And in this rather complicated graph with little images to show you what we found, not surprisingly, the best filtration, so 100% filtration efficiency, are these kinds of N95 masks that you've probably all seen. Some of you will now have. So these were great against volcanic ash, and we tried a couple of different kinds. Surgical masks fall around here, so 60 to 80% filtration efficiency. So they're quite good actually, but not as good as the N95 masks. And after that, you see this kind of downward slope as you try different kinds of masks, and you move from the multi-layered masks into the single-layered masks, and also different kinds of cloth materials. And so what you see right down here at the end is that ash from Sakurajima volcano, in this little blob sitting at 0 on the y-axis, the ash completely passed straight through this bandana. So the bandana wasn't at all protective against this kind of ash. Now we tried folding them into from 1 to 2 to 3 layers. It did improve the filtration efficiency a bit. We tried wetting the masks and the cloth, because a lot of agencies tell you to wet them, but that actually made the filtration efficiency worse. So we were very lucky to do this work and to really understand and then be able to tell agencies about the best kind of masks. And it immediately started having an impact with, particularly in Indonesia, NGOs trying to source these N95 masks to give to communities affected by eruptions. But the thing is that there are going to be times when N95 masks just aren't available. So, for example, in the midst of the COVID crisis, it was very hard to get the masks, but also when they're just simply not affordable. So, for example, even though NGOs in Indonesia might have been trying to source N95 masks, the local government agencies could not afford that and were simply distributing the types of masks that they had in their stockpiles, excuse me, which were usually surgical masks or other kinds of very thin mask materials. So this really brings an ethical dilemma. What do you do? Is some protection going to be better than no protection? Or should you only offer the very best and best known kind of effective protection? Well, these are well-known ethical principles in humanitarian support. The principle of effectiveness, of only offering the best protection, very much aligns with the humanitarian idea that you should do no harm. So you should not be providing interventions which are going to actually harm the people that you're trying to protect, and therefore you should only offer effective interventions. This is exactly why the World Health Organization did not and could not recommend communities to wear cloth masks for many, many months during the COVID crisis. The other end of the balance is the precautionary principle that some protection is better than no protection. Often this is the only intervention available. And what we have argued in the work that I did with Fiona MacDonald on this is that if that's the case, that's okay. You know, some protection is probably better than no protection. But the agencies who are providing the protection must inform the communities that they may not have a good intervention that they're giving them, that it may not be that effective, that people should not have a false sense of security. And so another aspect of my work has been to develop that kind of excellent communication with communities through my organization, the International Volcanic Health Hazard Network. And over time, we have produced many different kinds of products. We have produced videos and leaflets and all kinds, pamphlets, etc. But the important thing is that if you want that information to be taken up by the communities and to be used, and then for them to trust the source of the information, then it's very important that the communities themselves are involved in the development of those products. So I've also been co-designing these projects with agencies and with local communities. What you're seeing here is 2 images from a workshop that I did in Indonesia. Here you have a table of agency experts, and we're busy designing a video at this point, actually. And on a different part of the room, actually just behind them here, there's a table just of local women from the local community. Now, behind them is a table of men from the local community. And the reason that we separated them was because we knew in advance that women often did not have a voice in this particular community unless they were kind of separated and were allowed to speak. So we did what we could to basically be able to incorporate everyone's opinions so that the products that we eventually produced would be most helpful and most useful to as many people as possible. Now, I have a video that I could show you. I think because we started late and because I've been talking for a while, this maybe I'll show it at the end if we have time after questions. But this is the result of that process. And you can see just from the front that it involves a little girl. She's a real child. I know that sounds stupid, but what she's not is she's not a cartoon. She's not an animation. She's not an animal. And that's because the people in our workshops told us, no, she needs to be a real child. We're going to respond best to seeing real people in the video. And these were the kinds of questions that we asked in order for these videos to be used and liked. So if you're interested in the different products that IVHHN has produced, you can visit the website at ivhhn.org. You can watch the videos from there, and you can see some of the products that we've produced just on protection from ash here. So here's the product on how to fit a face mask. There's a video that goes with that. This was all before COVID, but actually has been used quite extensively during COVID. And you can see that these products are ratified by the World Health Organization, have their logos on it. So my take-home messages are that evaluating the risk of a health disaster in volcanic environments is extremely challenging. Impacts may emerge immediately, or they may continue for years, or they may not emerge for decades after an eruption starts. So a precautionary approach is really required at the time of the eruption to reduce people's exposure and therefore their future risk. This is really necessary in order to mitigate the potential health impacts. And that this involves really great public communication of the hazard and risk so that these impacts will hopefully be avoided. I should have said that we've translated our products, our IVHHN products, into many different languages. And if you're on the call or you watch this at some time and you see that these products are not in your language and you'd like them to be, please do contact me on the address here. So I'll finish the talk there. I've left some key reading here as well from the different aspects of the talk that I've mentioned. So if anyone is particularly interested, hopefully you can find out more here. Thank you very much.
Claire, excellent talk, very clear and informative. I learned a lot. Unfortunately, I have to run. So I've got a comment and a question. What you've described is part of what I talk about in the subject that I call the legacy of natural disasters. And your material certainly is the most important in that milieu of different disasters: earthquakes, landslides, tsunamis, floods, extended droughts. We don't understand what the long-term health consequences are, people being exposed to natural materials that they aren't normally exposed to. If you can't make any more progress in you, I mean, you've made more progress in your field than we have in any of the others. So we're looking to you to provide the guidance, the roadmap. So, and with your permission, I am going to use some of your slides in future presentations. My question is, a few years ago, I came across an article that indicated that clay coatings on quartz grains deactivates the quartz. Is that still a valid aspect?
Yes. So we don't see clay in volcanic ash, in fresh volcanic ash, which is why I didn't mention it. But as you know, we definitely see clay and quartz in association with coal. And you may remember, yeah, a few years ago, I actually had an undergraduate do a project on that. And I had an application this year from a PhD student to continue with that project. But unfortunately, he has not got the scholarships. But it is something that I'm hoping to get back into, and hopefully he'll find a way to come and study with me. He's from China. And if he had got the scholarship, I would have been on the phone to you and say, Bob, I've got this student, we've got to work together. And so hopefully that will happen. But yes, there's a lot more to do there, but I'm pretty convinced from the early toxicology studies that clay can dampen the quartz surface, the toxicity of the quartz surface, in the same way that I think the glass and the other minerals in the dome rock are likely dampening the cristobalite toxicity.
Great. Again, thank you so much. It was excellent presentation, but I have to run. So I'll be in touch.
Lovely to see you.
Claire, I voiced Bob's comments. This has been fascinating. This is a remarkable presentation. There's so much that we can learn from this. I mean, I'm a toxicologist, as you know, and there is so much that I have learned from what you have done in this particular topic. And I would be delighted to do a couple of things. I would like to put you in touch with my colleagues, my pathology colleagues, specifically the group in Puebla. They need to get to know this information and how to do these studies. This is fascinating information. As a toxicologist, I wanted to do, and also I just find so much of the direct application of this. You have been able to demonstrate how the work that you have done in looking at these volcanic emissions and characterization of this, on how to provide these unique outcomes of how to demonstrate the effectiveness of different masks. Specifically, it's so relevant to what we are going on with this pandemic. I should tell you from the public health area that no one, to my knowledge at least, have been able to use this type of information to demonstrate the effectiveness of masks that we use today. They have been basically being demonstrated in the public health, looking at issues like the type of material, this kind of things. We're not comparing with the actual effectiveness of the mask to retain dust, these kind of things. So I applaud your efforts in that area, because it's extremely relevant to society and to this particular area of COVID, what we are going through. And I saw the article that you actually published. It was in the UK media.
Guardian, yes.
Yes, and it was fascinating too. I sent that particular link to many of my colleagues to see how the information is, how you came up with that impactful application of this research. I wanted to also applaud you from having this unique understanding of how the community should be involved in designing, and even obviously in using, but even in designing some of these products and communication tools and all that. This is the way that we actual scientists should be looking into how the community should be involved, and looking at the contribution of the community, because they are the ones that actually are impacted by these events, and they are the ones that will be using these materials. So I applaud you by that, by that vision.
Thank you very much.
Involving the community that way. From the point of view of the content of some of the discussions that you developed, I am fascinated by the in vitro studies that you conducted, the cytotoxicity studies, because we have done that for many other, anthropogenic contaminants, and even some of the biogenic, contaminants as well. One of the areas that we have been working, which is very similar to this, is to using simulated fluids, either lung simulated fluids or the bile stomach simulated fluids, to demonstrate how many of these perhaps geo-available materials could be retained by the different organs or in the body. So there is a link between those two areas. I think will be unique to implement that in your project.
Yes, well, if I may say, my former PhD student, Ines Tomaszek, during her PhD, she's recently published this work. She used simulated lung fluids in leachate studies to see what came off volcanic ash in simulated lung fluids. Usually in a crisis response, we'll just use water. And she wanted to see whether actually simulated lung fluids would give a substantially different result from water, because it's hard for some laboratories to put together a simulated lung fluid, especially in a crisis. They may not have the right reagents, etc. And actually she found that water was not a bad analog. It gave a slightly conservative result, but it was okay to use water instead of simulated lung fluid. So that's one aspect of her work. And the other aspect has been to use co-cultures in her in vitro studies, so that we're not using a single monoculture of cells, which is not particularly reflective of what the lung is actually like. And these co-cultures, which include at least 3 different types of cells, kind of built in the structure of the lung lining, have given some really interesting results, and hopefully kind of are more reflective of the actual responses that would happen in the lung.
Yeah, that's wonderful that you have been able to do that, like integrating that other area of research into this. That's wonderful, because as you mentioned during your talk, this area of research is extremely difficult and complicated. And this is one of the things that I have on my lectures when I looked into the comparison between anthropogenic, occupational exposure, and then natural exposure to dust. And it's difficult really to research and to look at the biomarkers, even biomarkers that you can determine of early toxicity or chronic toxicity. So I'm glad that you really discuss and establish the complexity of this field, and how you have brought into that to some extent simplicity as well, on how to look into that. One study that I will suggest, and I would like to look into, because I know that there is nothing like this. And I got this idea from one of our colleagues that work with you very, very much, Ed. You remember Ed Derbyshire? Ed was fascinated by the way in which we looked at registries, registries of mortality, is particularly with looking at dust. So if we can actually link some of these studies to look at registries, that we can do some retrospective studies, that might give us a little bit more insightful information about the long-term chronic exposure in populations that are exposed to this kind of events. I know that the accessibility to that type of material is practically impossible.
Yeah.
But it will be something that it will, perhaps just looking at the registries, clinical registries available in these communities, could give us some information on that we can link with the geochemistry, with the in vitro toxicology, or that. So that would be something that, I kept that idea from Ed. Ed was the one that actually gave me that idea of looking.
The thing is, it's really good to also have exposure data, so that you can actually link any findings to be certain that those outcomes are related to the exposure to volcanic ash and not to something else. The problem is that it's so rare to have exposure data collected at the same time. Air quality monitoring around the world is improving, but retrospectively, there's very few places where we have sufficient exposure data to be able to link health outcomes to the eruption itself.
Right. And always my last comment here, also from the content, from the science content, will be to, and I think you alluded to some of this as well, is how we can. I mean, it's important for us to really develop risk assessment, protocols that we can actually put in place. Obviously, those will be risk assessment type of protocols for acute for acute exposure. I'm sorry. So I follow that part of your talk, and I think it's going to be really interesting to do. I see that as a research gap. One of the things that we don't have is this risk assessment paradigm that we need to develop.
I think that's right. And, the problem with doing a full risk assessment is that you really have to already have data from exposure assessments, hazard assessments, etc. But one of the issues with, I guess, the clinical studies that have been done to date is that different locations and different groups have used completely different study designs. So even the data that we do have are very hard to compare among locations and eruptions. So one of the things that we did quite recently is we published a protocol for future epidemiological studies. So there would be a kind of off-the-shelf method that people could use, so that, when there's an eruption, we've got 2 different study designs. They can choose which study design to do. They don't have to go through the study design process. It's much faster to get ethical approval, hopefully to get funding as well. And, it's to speed up the process in eruptions, but also if people start using those epidemiological protocols, then hopefully in the future, we can actually start to compare among different eruptions, because the problem we've had is that all these different methods out there, and they all use completely different outcome measures, etc. It's really hard. So
right. No, that's you provided one step there, very important, which is the risk management of these exposures, and I think that you at the end of your talk, when you look at all these products that are coming out of this particular work, then you also provide a part of the answer to this by discussing preventive measures. So it's everything. You did a fantastic combination of all this of all what we need to know and do for this type of event, exposure to these events. And I personally am so grateful to you for giving me the opportunity to listen to this fantastic, remarkable research.
Oh, thank you. Thank you very much.
And all this will remain in the recording that we have done. And although most of the people that attended have already left, but it will be in this recording for people to download and to study further. So you had people from several countries attending your presentation today, and I'm sorry, I know that it's going to get widespread use. So personally, thank you, Claire, for giving us that opportunity of listening to you. So if there are no other questions, maybe we can watch your video, because it will be we should keep that also as part of the recording.
Yeah, certainly. Just give me a second. My PowerPoint just crashed a second ago. I don't know why. So now I've got to open it up again. Oh, here we go. Right, 1 second. Security alert. Right, okay. I will share my screen again.
Okay.
I think what may have crashed it is the video, because the play button's no longer coming up. So I'm just going to go to the internet and play it directly from there. Okay.
Okay.
I think there's
Over 1 million people have fled their homes to escape conflict in Ukraine. Millions more are expected to follow. They've left behind jobs.
We don't see the video.
You don't see the video?
Let me see. Let's see.
Go to share again.
Let's see if we can go back to the.
Can you see it now?
Yes, we can. It's coming up. It's coming up.
Okay. Tell me if you can hear this.
Yes. Yes, we do. Yes, we do.
Breathing volcanic ash can be uncomfortable and may cause serious health problems for some people. You may want to reduce your exposure to volcanic ash, or may have been advised to do so. The best way to reduce exposure, especially for sensitive people, such as children and infants, older people, and those with lung and heart conditions, is to shelter somewhere which is not ashy, ideally inside a building where you can stay indoors for some time if necessary. If you are very concerned about your health, take advice from a health professional. Try to keep the ash outside. Use just one entrance to the building and leave ashy clothes and shoes outside. Close doors and windows where possible. Try to seal up large gaps and spaces to the outdoors. You can use tape and plastic sheeting or rolled up towels. Do not use air conditioners, which suck in air from the outside. Don't use vacuum cleaners as they can blow out fine ash. If you stay indoors for a long time, make sure that the indoor environment does not get too hot. If it gets too hot, consider moving to a safer place. Don't use cooking or heating stoves or anything which produces smoke or gas. Do not smoke cigarettes or other products. Once the ash has settled, it is important to remove it through cleanup activities, using water to dampen it first, or waiting for it to rain. You should wear a face mask if you are cleaning up settled ash or if it is thrown into the air by wind, cars, or other activities. People with lung and heart diseases should talk to a health professional about whether face masks are suitable. When you wear respiratory protection, the effectiveness depends on how effective the mask or material is at stopping the ash from passing through the material, and the fit of the mask or material to the face so ash cannot enter around the edges. Care should be taken to ensure that it is not harder to breathe when using any form of mask. The most effective respiratory protection for adults is to wear a well-fitting, industry-certified face mask, such as an N95 mask. The certification will be printed on the mask. Such masks are usually disposable. They may feel uncomfortable because they need to fit tightly. These masks can come in many different shapes and sizes. Some have a valve on the front to improve comfort by letting hot, humid air out. A surgical mask works well as long as it fits well to the face. If it does not, it will provide less protection than an industry-certified face mask. You can improve the fit and effectiveness of any mask by tying a layer of cloth over it, although you're likely to find this less comfortable, and you should not tie the cloth so tight that it makes breathing harder. Simple healthcare masks do not work well and also do not have ways to make a good seal to the face. Scooter, fashion, and hard cup masks do not work well compared to the industry-certified and surgical masks and may not fit well to the face. Cloth materials, for example bandanas, t-shirts, veils, and handkerchiefs, do not work well and they also tend not to fit. Adding more layers of cloth will help, but cloth will still be less effective than most face masks. Wetting a mask or cloth does not make it work better. If you give a mask to a child, show the child how to fit it well, and be very careful it does not make breathing difficult. Most masks are too big for children and infants, so they should stay in a non-ashy place if possible. You should check your mask often for any damage or growth of mold. Some industrially certified face masks have a use-by date printed on them. After this date, the manufacturer cannot guarantee the quality of the mask. Disposable masks are designed to be used once only, so packaging will often state that they should be thrown away after 8 hours. But they can still be worn until you notice that they are clogged or breathing becomes harder. Masks should be worn when you are awake. It is not recommended to wear a mask while sleeping, as it will probably not stay fitted to your face and it is harder to breathe with a mask on. If supplies are limited, disposable masks can be stored for reuse in a clean bag or box to keep the inside of the mask clean. They should not be hung in a dusty environment. For further information on the health hazards of volcanic ash and preparedness for ashfall, please download the IEHSC pamphlets available at the IEHSC website.
Thank you, Clea. That was a great video.
Thank you.
Is there I'm going to ask Jesus later on to test that we can actually have the video included within the presentation. But if there is a problem with that, will you be able to provide us with a copy of the video separate that we can also incorporate into the database for the presentation?
I think so, or it can be, you can include the link from YouTube. That might be easier.
That might be easier. Yeah, that's great. Fantastic. Yeah. So, are there any questions from the audience?
No.
Okay. So, Claire, thank you again. The presentation was outstanding. We are going to send you very soon a message with all the links to the different recordings, so you can also distribute that to your students and colleagues as well. Okay.
Thank you. Great. Thank you very much.
Thank you.
Thank you. Have a great
Congratulations.
Rest of the week. It was great to see you again. And thank you so much for giving us this opportunity. It has been a fantastic seminar. Thank you.
Yep.
My pleasure.
Thank you. Bye-bye.
Bye-bye, Claire. Bye-bye.
Thank you.
Bye.
Bye-bye.
Thank you, Jesus.
You're welcome.
We
Bye-bye.
will talk soon, okay?
Jesús, okay.
Pronto hablamos sobre esto porque para que comience a redactar el link.
All right. Okay, perfecto.
Muy bien, pues cuídate. Nos vemos entonces.
Okay. Gracias. Hasta luego.